Hey everybody, so this is the third video on wave motion where we're going to go over a few of the extra problems that are at the back of the PowerPoint. So you can pause the video right now and work on this problem. We'll go over it in a second. Okay, so here what we have is they want to know what are the wavelengths of that's being shown here. So here, this is something different than what we had before. Before, we had an area where we were fixed at two ends, but now this end is free to move. What this is going to mean is that the standing waves that we create have to have a node here and an antinode over here. So if we look at the waves, so we have a wave being produced here. I'm just going to make a big wave like that. Our node is here. Now our antinodes are going to be at this location, this location, this location, and so on and so on. This is a quarter of a wave away from that node. This point, on the other hand, it's not a full wave away, it's 3/4 of a wave away. And you should start to see the pattern. 3/4, 5/4, so on and so on. So essentially, within the length provided, we can fit some integer quarter of waves provided that that number is an odd number. That's pretty much what it's trying to say. Now, I rewrote that equation a little bit differently for this. What I did was I rewrote that whole n part so that I can change it so that the number n was just any number, 1, 2, 3 positive numbers, as opposed to only odd numbers. Now you can do this. This is fine. If this is what you want, be my guest. But I would just say that first, when you do this, you have to make sure that you include what n is supposed to be equaling to. If it's equaling all the positive numbers or if it's equaling all the odd numbers. Another thing that I would recommend is I would actually recommend that you stay like this, mainly because of the fact that I don't know why they do it, but when you have a standing wave that looks like this, they, instead of calling, so we mentioned before about how you have the fundamental frequency and then the next biggest wave that can be produced is called the second harmonic. First, that's only true when you have the case of fixed end and fixed end. But when you have a case that's fixed and then free, so like node to antinode, you end up getting where instead of the next next frequency is usually called the third harmonic, and then the fifth harmonic. So they actually do call it odd numbers, so it might actually be easier to write it like this. Like I said, it's whatever the question is dealing with. Alright, here's the next question. You could pause the video and work on this yourself. We'll go over it in a second. Alright, so what we want to do is they want us to figure out the amplitude of the wave. Now at first, it may not seem like we have enough information. However, what we have to do is first, they give us a frequency and a wavelength. I can use these two numbers together to figure out what the actual wave speed is. So using v equals f lambda, I get that the wave speed is 22 meters per second. Now, here's the key thing. It tells me that the maximum speed of the particles is the same as this. And then they're using that to refer to the amplitude. Now, if I think back, remember the previous lecture on simple harmonic oscillators is related to this. It's the foundation for this topic. So we can actually take this wave and just relate it to a simple harmonic oscillator. And in that case, we do have a way of relating the max velocity to the amplitude of a wave. If you remember, it was this equation. Vmax equals omega, the angular frequency, times the amplitude. Moving the terms around, we get this, plugging 2 pi f in for the angular frequency. We end up getting this. This is actually what it simplifies to. And we get that the amplitude is 1.6 centimeters. Now, this is a little bit serendipitous, and it's mainly only because of this, that the fact that the max speed is equal to the wave speed. But it is interesting to see that the amplitude actually seems to be related to the wave number. So if you remember, this is actually equal to the 1 over the wave number. So it seems like the amplitude is 1 over the wave number. But again, only in this specific case. It's a little bit of serendipity. All right. And then this question. I want to just note they want you to estimate the average power. And then down here, what they're saying is you have to estimate the adult chest in order to find the power. So I just want to point out that you are looking for the average power here. And you're going to estimate the area of an adult's chest to find it. So you can pause the video and work on this yourself. We'll go over it in a second. Alright, so we do have an equation for average power. The equation is, well, first, in order to figure that out, we need to actually find the frequency and the velocity. So with the period to invert, we take the inverse of it and we get the frequency. Using the wavelength, we can then find the velocity. Then we can combine it all together into the average power equation. The key thing here is this is the only thing that we weren't given, but you just kind of have to eyeball it. You know, a person's chest is about half a meter. Vertically, it's a little bit less than a meter. So yeah, 0.3 seems to work. I'm sure you could have looked online to figure out what the surface area of an adult's chest is. But yeah, this would be what numbers you'd use. So you'd end up getting an average power of about 18 watts. All right. That's about it. So if you have any questions, please let me know. Otherwise, I'll see you in the next video. See you later.